My name is Daniel Withopf. In case you don't know me, I work for the German car supplier Bosch, mainly on self-driving vehicles and driver assistance. For the talk today, it's a bit interactive, so feel free to ask any questions while we edit. So if you have a question during the slide, ask it. I also have 1 or 2 questions for you, so it would be great if you could participate a little bit. There are no incorrect answers, so it would be great if you can help me out. But first, to something completely different, adaptation to the environment. Does anybody have an idea what this little fellow here is, what kind of animal it is and where he lives? Sorry? Bear? Bear, yeah, almost, it's close. You can. Arctic fox, exactly. Yeah, you already solved it completely. I wanted to give a small hint. It's how he looks in summer. This is how the guy looks in winter. So that's his winter skin, pretty furry, but yeah, he can live fairly high up north and at really cold temperatures. So he's perfectly adapted to the environment he lives in. I have another one. Does anybody know what this animal feeds on? It's an aardvark and feeds on ants and termites. Yeah, you can probably tell from the long nose. I have a second one, but that's maybe even easier. This one here. Giant anteater, yeah, he feeds on ants. So as you can see, they've perfectly adapted to what they're eating. They wouldn't probably get to the ants if they didn't have that long nose. And the last one, that's fairly self-explanatory, giraffe with a long neck. So it's fairly obvious they can eat pretty well like that. Although I think there's some discussion with biologists whether it's due to the fighting, because they also fight with their heads. So it might have an advantage if you have a really long neck because you can hit harder, or it's because they want to eat from the pretty high trees. That's the other explanation. Good, so what am I aiming at? Like every species in nature adapts to the environment. Just like that, our code also should have to adapt or should be adapted to the environment in which it runs and under which you want to use it. So brief overview of my talk. I want to talk a bit about boundary conditions that can influence our code. So I'll give a few examples and explain what that means. And then we'll delve into more details for 3 of these. The first one is performance versus latency. The second one is deterministic recomputability. You might have never heard about it, so I'll explain what it is and why it's needed. And last but not least, that will be the biggest part of the talk. How can we replace dynamic polymorphism? That's sort of a bit coming from my environment. So the embedded domain where you often cannot use dynamic memory. And then, yeah, you want to maybe do something that's similar to OOP, object-oriented programming. And then you need a replacement for that. And there I'll explain how multilevel CRTP combined with a state variant works. This is something that you rarely find. Classical CRTP, 2-level is fairly easy. You can find it everywhere. But the multi-level case, you cannot find many resources on that, so I'll talk about that in detail. And as I said, feel free to ask questions anytime. Good. First of all, brief prelude, coming a bit from the talk by Kate Gregory at the beginning of the conference, that most of you probably have seen. She talked about the experiences we make and how we can use these and apply them in the future to hopefully become better programmers. So for me, there are 3 levels of enlightenment in C++ programming and maybe even in life. Level 0 is we make the same experiences and probably mistakes over and over again. I hope we're all past that, or we at least want to get past that. So we should all be at least at level 1, meaning we are able to learn from our experiences. But in my opinion, the true enlightenment comes when you've reached level 2. And this is probably a continuous journey, which means level 2 is being able to judge which of your experiences in the past actually apply in your current project and which don't, and what this means for the program at hand. Because often we've made several experiences if you've worked for quite a long time, and no 2 projects are ever the same. So sometimes we have a slight change of preconditions or boundary conditions, and that might already mean that you have to throw away your experiences or at least adapt them to the new problem and come to a different solution. Sometimes a completely different solution. Sometimes it's just a tweak, or in some cases, maybe you can even use the same thing. But in my opinion, no 2 projects or problems are identical. So it's rarely the case that you can exactly take over a solution from the past and apply it to a new problem. So that means before we start any project, we should always try to understand the preconditions and the environment in which we work before we actually start working. Or if you can't, then maybe as soon as possible while you begin working. This is really important because it might bring you to a completely different solution in the end. Good, now a few examples of boundary conditions that could influence the way we code. Of course, that's not exhaustive, the list, that's just the ones I came up with. I'm pretty sure every one of you knows a few more. First question might be, what are the compile times of your whole project? Is it a 5 minutes or 2 hours? This could influence the whole integration strategy that you're doing, for example, or your CI checks. You usually work with pull requests, I guess, everyone. And if you have 5 minutes build time, you might manage to just build each pull request after each other, so building on the previous ones, so that you can't have any semantic merge conflicts. But if you have a build time of 2 hours, that might be pretty hard. So you might be forced to do parallel builds and then live with the fact that you might have semantic merge conflicts when that gets onto main or your develop branch. Another example, are you running in the cloud or on an embedded device? In the cloud, yeah, it's fairly easy. If you need more runtime, you just order a bigger machine or 5 more machines. It costs money, but you can do it, and it's no big problem if you run out of your runtime budget. On an embedded device, on the other hand, you usually have a fixed runtime budget. You can't sort of increase the box that you run on. You have safety requirements in some cases, and often also requirements on how you handle memory, whether you're able to use heap memory or not. Then another question that might be interesting is whether throughput or latency is important for your problem, because this might influence the optimization strategy and even the design of algorithms, whether you have to design for the worst case runtime to make that as low as possible, or whether it's okay to design for the average runtime. So it depends on which problem space you are in. Then there's another question, whether we have to produce identical results in each run, especially when you resimulate something. So if you have a robotic system that's out in the wild, and you might have a recording when something happened, then you ideally want to be able to reproduce the problem, even if it's a really rare one. Meaning you should be able to produce the exact same result that you've seen out in the wild. And this, as we'll see later, influences class design, scheduling that you run in your system, and also how you record data and what you're recording. Another important question or boundary condition is what the implications of a bug are. Can we just terminate the program in case of an error? I don't know, if you have your mobile phone and an app crashes, no big problem, you restart it. If you're in a car driving 100 kph, I don't think you want to have somebody terminating the program. Sometimes there's a fallback solution, but if the main solution had a problem and ran out of memory, why wouldn't the fallback solution run exactly into the same problem? So you have to design your system to be forgiving and ideally not run into these errors in the first place. And last but not least, can dynamic memory be used? As I said, this is often in embedded domains. That you can't use dynamic memory due to safety or runtime considerations. This influences, for example, container design, how you can store your things. It influences move semantics, so you can still use move semantics, but you might just not get any benefit out of it if there's no heap memory that you could sort of transfer. And it also influences class design and how you can use polymorphism, or whether you can use polymorphism. As I said, the list is not exhaustive. Feel free to add the points that are important in your domain here. So I want to go into details, as I said, in 3 of these topics. The first one is throughput versus latency. Second one, the deterministic recomputability. And the last one, how we can work without dynamic memory allocations and what that means for your code, your programs, and the whole processing chain. It's a little bit tailored to my domain, but I hope everybody can take something out of that. It might be relevant for all domains. So let's move on to throughput versus latency first. So imagine you have 2 different system designs. The one on the left-hand side has a fairly low runtime in each cycle, but every once in a while, there's one cycle where the runtime has really a big spike, so you have a really high runtime. And the system on the right-hand side has a bit of a higher runtime, but it's fairly reproducible, so it has almost the same runtime in each cycle. So another question for you, which one of these two system designs or runtime behaviors would you prefer for self-driving vehicles or for high-frequency trading? Yeah? B for self-driving was the answer, and A for...
B for, so first diagram would be high-frequency trading, because
yeah.
you want to be as fast as possible.
Yes. So the answer was first diagram on the left-hand side would be high-frequency trading, exactly, because you want to be faster than the other ones, you want to beat the market, and you could probably detect when you're in that case when it takes fairly long and then you just don't emit an order, and that's hopefully fine, you don't lose any money, don't make any money either, but yeah, fine with that. And for the right-hand side, what was your answer? Then guess?
Well, I would say the other one.
Yeah, exactly. So the other one is usually good for self-driving vehicles, because if you have a fixed cycle time in which you have to output a control output to your controller, and you take too long, then there will be no output, which might be bad. I mean, if it's one cycle, you might be able to live with it, but usually you want to have a fixed cycle time that you can meet, otherwise you really run into problems. So the right-hand side is probably better for anything where you need a stable response time, so low latency or deterministic latency in that case. Probably, the best word. I don't want to talk much more about this. There's a really nice talk by Timo Dumler, who's also at the conference here, what is low latency C++. It actually has 2 parts, so 3 hours talk from this year's CPP Now. It's a really nice talk. I also took the inspiration for the previous slide from that talk, so please watch that if you're interested in the topic. It's a really great talk. I should mention it's not yet out on YouTube currently, but it should come out soon. So for anybody watching on YouTube, you'll probably be able to find it. For you in the room, it might take a few more weeks. Good, now moving on to the next topic, which is deterministic recomputability. A really difficult term, maybe I should have picked a simpler one. So let's just assume, we have a robotic system, self-driving vehicle out in the wild. There are test drivers maybe driving in it, or the robot drives around. And then if you observe a frequent problem that occurs every minute, if you have a recording of that, then it's usually fairly easy to reproduce that at your desktop machine. Yeah, you just rerun 5 minutes and usually it will just occur. And hopefully you can debug the problem and also fix it. But now let's imagine a problem that occurs once every day of runtime. So this is probably already a lot harder. You have to be lucky to get a recording of that, and then you have to be lucky to actually be able to reproduce it on your machine. And what is, if this were a problem that only occurs once every month of runtime, then even if you have a recording and if you're lucky, it appears on your desktop machine. If you're unlucky, you can't reproduce the problem, so you have no clue what's actually going on. This can be really, really difficult. So for these systems that are safety relevant, it's usually really important that you can reproduce all kinds of errors on your machine or maybe on the same hardware. That's probably the best choice. If you can rerun the system on the identical hardware, that makes it way easier. Now, as I mentioned, when you rerun the system with a recording, the algorithms might just produce a different result in a second time, and then you're out of luck. Does anybody of you have ideas what might be the cause for such non-determinism or for different results when you rerun the system? Yeah.
It's usually very hard to capture all of the state of the program. So even if you have data dumps, they may not recreate the exact state that leads to the error.
Excellent answer, so the gist was it's really difficult to reproduce the state of the program, so the whole state, because you could either rerun from the very beginning when the thing has been switched off, but it might have been running for 10 days. You don't want to resimulate 10 days. And then it's really difficult to produce the exact state. That's correct. Another thing, Peter?
Timing differences, address layout, cache misses
Yeah,
also.
timing difference, exactly. Yeah, that's really easy to have a different timing or just a different scheduling. So that's also my first point, different runtime behavior due to scheduling, executing order, or fair amount of other reasons. stateful classes, this is sort of what you mentioned, the second topic. So it's usually in OOP, we have a lot of stateful classes, and it's really difficult to serialize all of that into a recording and just record what is needed, but not too much. I will explain later how this can be done, but it's definitely a challenge. And also something innocent as a random number generator has an internal state. So if you don't make sure that you store the seed or you always start with the same seed, then you would also end up, if you use a random number generator, you would end up with a different output if you rerun something. So this is a sort of an example of hypothetical runtime behavior. So let's assume we are in a robotic system. We have input A and B, usually sensors. They record at a certain time. And then usually each sensor data has a pre-processing, so pre-processing A and pre-processing B. And then we have our component C, which is responsible for integrating the sensor data. So maybe a sensor data fusion algorithm that runs in component C and is scheduled maybe every 50 milliseconds. Now in the first example here, pre-processing A is finished when we first run component C, meaning component C sees the input from sensor A. And for the second run of component C, pre-processing B is then finished and component C can run with the data from sensor B. So this is sort of what might have happened in the live system. And next, when you resimulate, due to some randomness or runtime effects, it might just be different. So this time, pre-processing B finishes first. And component C also gets the input data from sensor B first. And in the second run, we only see the sensor data from sensor A, meaning we now have a different order of inputs. And this, depending on your system, could already significantly change the output, or maybe it's just small differences, but this might be enough that your bug does not appear anymore. And then you're really out of luck. So do you have any idea how we could make this deterministic? Sorry? Make it serial, that's an option, yeah. In simple system, that's probably also the best choice. But if you have, I don't know, 20, 50 sensors on your car that you all have to integrate, then it becomes really difficult because you would have to know when the sensors fire, actually control the sensors appropriately. They couldn't have any delay, so they would also always have to produce the outputs at a fixed time cycle. This could be doable, but it's usually really, really complex. So in general, that doesn't work. But there is a slightly a thing how we can make at least one component, or in the end, even the whole system reproducible. And that is if we simply record the inputs for component C. So we say, okay, in that first cycle, it ran on input A. Next cycle, at that time point, it ran on input B from the sensor. And you usually also have numbered the input. So you know this is the, I don't know, 550th input of that sensor. And then later on, when you rerun only component C, you have all your input data in your recording, and then you can pick the appropriate input data, trigger your component with the appropriate inputs, and ideally you should get identical output if all the other conditions are also satisfied. Good, now we already talked about, yeah, what was the question? Yeah, this is when you replay a recording and you want to have ideally bit identical output for one component or even for the whole system. And then if you've recorded these, yeah, which inputs were used in which cycle, then you at least have a chance to achieve that. Good, the second part that we already mentioned earlier is like the stateful classes that you have in classical OOP. Let's assume we have an object tracking algorithm here on the left-hand side that contains an object list manager. The object list manager has the object list, of course. It might also store the measurements that came in the current cycle and our famous random number generator maybe, because there's a randomized algorithm that does association, for example. Then the object list is just a list of objects in our simple example, and the object itself is represented with a state vector and a covariance matrix. Now you can already see that we've hidden quite a lot of state in all of our classes. And if you run that with a middleware or some recording device, it's really difficult to find out what is actually needed, what is the actual state that lives over time, so between different cycles, and which is just a temporary variable that you don't need to store. For example, the measurements, they're probably recorded as an input of your component, so you don't need to store them again. The random number generator is important on the other hand, and also the object list, because this is the state that you want to filter over time and that you need to store. Now, if you want to make that a bit better and easier to record, then it often makes sense to move a bit more towards a functional programming style. So not use that many classes, or maybe classes with static methods and no members, but that's effectively free functions. So if we would change that to a free function system, then we would on the left-hand side have all our inputs. So these are the measurements. Maybe you need the ego motion of the vehicle. I didn't include that up there. And the object list. And if you have your random number generator, that will also be an external input to your component. And then if you have a middleware that is able to record all these inputs, that's the first step to becoming reproducible. So we can see the state, our object list, is an input, and at the same time, it's an output at the very end of the algorithm, so it's being fed back in the next cycle. And you can also see that, for example, the predict method, which predicts your objects to the next cycle, only needs the object list and the ego motion, while the update function that does the actual update with a measurement uses measurements, ego motion, and the object list. And in the end, you usually also have an output that might not be identical to the state. So usually the state is a bit more, and the output is just what the next component that wants to react on your output actually needs. So that might be a bit reduced. And yeah, as I mentioned, if we have a recording of the runtime behavior and of all inputs and the outputs, then we're usually able to reproduce, do bit identical reproduction of the problem. If your simulator is perfect, if you're running on a desktop, or the best bet here is probably to run on the original hardware so that you don't run into any differences between floating point calculations or other things. Good. Any questions here so far? I guess afterwards I'll move on to the next one. Good. Then to the biggest part, programming without heap allocations. First of all, a few facts about classical C++ programming and dynamic memory allocations. So in general, allocations can take a relatively long time due to, for example, memory fragmentation, because the memory is usually managed in linked lists. So it might not be really quick, or at least not as quick as if you allocate something on the stack. That's just incrementing or decrementing the stack pointer. On the heap, there's a bit more work involved. Furthermore, your allocation could even fail despite having enough memory when you have fragmentation. So if you don't have a memory block free that's large enough, then you might not be able to allocate any memory, even though there would be, in theory, enough memory available. And last but not least, the allocation can also fail completely because the heap is actually full. So that even if it were like consecutive free part of the memory, you can't fit your data block in there, and then the heap is full. And this is usually, this gives you an exception, and in embedded domains, we usually want to try to avoid that at all cost. Running into the situation where you have an exception, and then you basically can't do anything because your heap is full. This is not a good situation that we want to be in. That's why usually dynamic memory is often forbidden in safety critical applications. So it's not impossible to do it, but if you use dynamic memory, you would have to have a really good argumentation why it's safe, and also sort of prove that and ensure that it's actually safe to do that. There are also sort of solutions in between. Sometimes it might be okay to do dynamic memory allocations at startup when you bring up the system, but afterwards you don't do it, or you say, oh, I don't want to do it at all. That's also an option. Good. Now, assuming we actually have to program or want to program without dynamic memory, what are the challenges that we are facing in that case? First challenge is, how can we store objects with varying types and sizes, for example, in a container? With heap memory, it's really easy. You just create it on the heap, and then you store a pointer to the object in your container. That's really easy. But if you only have stack memory, it's a bit more complicated. Then we might also want to use something like virtual polymorphism. So we would need a replacement for that. It's not completely impossible to use virtual polymorphism with static memory, but in the end we'll see there's a better way to do that and achieve almost the same thing. And last but not least, how can we implement multi-level inheritance hierarchies if we are moving away from virtual polymorphism? And last but not least, don't even get me started about move semantics. As I said, you can still use them, but if there's no resource, heap memory, meaning in that case, in your classes, it's really difficult to be able to reuse anything. You could reuse file handles or something, memory on the heap. That's something that you can reuse with move semantics. But if you don't have heap memory on the stack, there's no way how you can reuse the memory on the stack because stack's managed automatically. Which means you can use move semantics. There are also other nice use cases for which you can use it, but you can't use it for being efficient, sort of what you get in your average YouTube talk about C++, where they often say, okay, yeah, with move semantics this is efficient, which is true if you have dynamic memory. If you don't have it, it might be different. So you always, again, one of these preconditions where you have to be careful and understand what it actually means and what implications that might have on your program if you don't use dynamic memory. Good. First of all, let's see how we can create objects of varying sizes with dynamic memory. That's fairly easy. Yeah, we use a state vector of shared pointers to our base class, and then we just call make shared for derived class A, derived class B, and we push that back into the vector. Yeah, really easy. Yeah. Question?
Can I ask a question why you use shared pointers and not unique pointers?
Just for the slide, unique pointer would be just as fine. Yeah. Question was, yeah, why I use shared pointer, not unique pointer. Yeah. Usually unique pointer is probably the better choice. Yeah. Good. Without dynamic memory, it's a bit different. So let's assume we have a static vector. So this is a vector that does not use heap allocations with a fixed size. This is something that you usually need when you want to work without dynamic memory. And let's assume we again have 2 or n derived classes that we want to be able to store, and we have a maximum of 100 objects. If we now have 2 different classes that we want to store, we usually have to have 2 vectors with a capacity of 100 each, because we don't know, we might just need 100 objects A or 100 objects of derived class B, or it's a mixture. But if you don't know that beforehand, yeah, you need quite a lot of memory overhead to achieve that. But fortunately, there's a better solution with C++, the variant data type. So we can just say, okay, we have a stat vector of a variant of derived class A and derived class B, and then you only need the 100 elements, and it will just occupy the maximum storage of your classes that you want to store. Yep.
Just use the variant in our project.
Yeah, we will use it a bit more later on. So.
It's not necessary in embedded system. You can use it even a bigger program. No?
Yeah. Good, so let's see how we can work with these variants. So this is a fairly easy example. So we're still in the virtual function example here. So we have a base class with a virtual method foo that just outputs its name, and also derived A, derived B with the same method. So both derived classes are overriding the method we specified. Then we create our vector with a variant of derived A and derived B. We push back one derived A, one derived B. And then we iterate over our vector, call statVisit, accept the base class reference, and we call base foo, and this simply produces the output that you see here. So you will get the output from derived A and derived B. Fairly easy. But now the question is this really efficient? So we're already using a variant. So there is one dispatching at the beginning, and after you're through that dispatching with statVisit, it's clear which type we actually have. So we know the concrete type, and then we're still doing virtual dispatching, which is sort of, you can do it, but yeah, it's just overhead that you don't really need in this case, because as I said, the statVisit does some virtual dispatching or something that's similar to virtual dispatching. And then we're sort of more in the static dispatching case where you know your type. So there's no real need to work with virtual methods here. Now you might all know there's a replacement for dynamic polymorphism, the curiously recurring template pattern. There's also a few blog posts if you want to look it up online. The base form of that is fairly simple. So we have a base class that is templated on our leaf type, so the derived type. And we can create a method, do something. And in that method, the pattern usually casts to the derived class. So it casts to this pointer, or you access the this pointer, and then you cast to a reference to the derived class. And then you can call a method on the derived class. And the derived class then specifies the content of that method, which is usually a customization point or something similar. So that's fairly easy, and you can see it in a lot of talks. But what is rarely mentioned is how this generalizes to more than 2 layers. So this 2-layer case is fairly easy. But if you want to do an arbitrary number of layers, then it can get a bit more complex, and it's really difficult to find any resources online about that. Yeah, so the question is, how can we handle more than 2 levels of that? And yeah.
Ask the question, why do you want more than 2 levels?
Good question. Why do you want more than 2 levels? The question is whether you already have implementations in your base class. If you already have some base implementation, I mean, it's the same with virtual polymorphism. Sometimes you want to have more hierarchies. No. It depends. Yeah. Sometimes you can, well, for us, we have in state estimation, we sometimes have a hierarchy where you have Cartesian and polar states. This would be the first distinction. And then you have a specialized version of that. So 2 to 3 levels we observed. We haven't had like 5 or 6, so you're right. I also don't assume it makes sense to have more than 3 or 4, but 2, okay. Let's see. Good, so let's see how we can generalize that from 2-level to multi-level CRTP. So in the easiest case, as I said, we have a derived class, and that inherits from base with derived as a template argument. This is the simplest case. And now if we want to generalize that to 3 layers, maybe it just looks like that here. So we have derived class that inherits from middle derived. And then this one, in turn, inherits from base with middle and derived as a template argument. This might sort of seem like the straightforward way how you can implement that. But please forget this pattern. You have to do it slightly different, otherwise you run into problems. As we've seen on the last slide, there's a static cast in the base class to the template argument for the derived base class. And if you do that, you would just end up in the middle part here and not in the most derived leaf class. So this here, it can be made to work, but you need boilerplate code and it gets complex. So what you should do instead, if you ever need more than 2 levels, quoting Peter, is to have your derived class that inherits from middle with derived as a template argument, and then that inherits from base with the most derived class as a template argument. So you always pass the sort of the leaf class of your inheritance tree all the way up to the base class. And yeah, as I mentioned, it's really difficult to find any resources on that online. So there's one Stack Overflow post. You have to be lucky enough to not pick the highest rated answer, because that would give you the middle design. You have to pick the second highest rated answer. That gives you the right-hand side. And by now there's also a nice blog post by Jonathan Bocara that explains this. In the beginning, he also explains the middle part, but at the very end of the blog post, he comes to the right-hand side and also mentions that this is the best or easiest way, at least, to implement the whole thing. Good. I now want to show a bit of code, how we can implement that and what implications that might have for our code, what it should look like. So, as I said, we have our base class. We have the type middle that inherits from base with leaf as a template argument. And we have our most derived class that inherits from the middle type with derived as a template argument. I always have to be careful not to say middle class, but yeah. Maybe it's the middle class. Good, then in the base class, we have a helper method, leaf, that just converts to the most derived type. In real code, you probably should also have a const version of that. For the slideware today, I just left out the const correctness. So ideally, it should be 2 methods, one non-const and one const method. Then we have our foo method, which sort of acts as our interface to the outside. So this is sort of the interface that all of these classes here satisfy, and you can call that from the outside. And the content just does a cout for our experiments later on, and it calls the most derived foo impl method. So these impl methods are providing the actual functionality. In this example, yeah, we have 2 foo impl methods, one in our middle type and one in the derived type. We make these private so that nobody from the outside can directly access these impl methods. So the only way to call something is via the base class, which is how it's supposed to be. And then we also have to befriend the base class to be able, so that the base class can actually call something from our other classes. So yeah, you could leave out that private thing, but I think it makes sense. We want to have a common interface for all our classes that's in the base class. So it probably makes sense to protect the rest or hide it from outside users. Yeah. Good, now let's see what's actually happening. So we are in main, and we're creating an object of our derived type, and we call the foo method. This then dispatches up to our base class, get an output of base foo. So down here, you will always see the output on the console. And then we call leave foo impl. And does anybody have an idea where we end up in that case? Derived, yes, correct. So we'll always end up in the most derived version of that method. So number 3 here. And you can also see the output down here. Now, if I were to remove or comment out the implementation in derived, of course, we would end up in the middle class and yeah.
Private?
Yeah, because we befriended the base class.
Yeah, but you have a derived class that is unable to call the middle class.
Yeah, it's not the derived class that's calling it. We're calling it from to up here, and that's dispatching to that middle. If I'm not missing something here, but.
Protected, yes, but it's private. That should compile.
Okay, it should. I'm not sure if I ran exactly this one, but I think it does compile because it goes via the base class. But yeah, no guarantee. I'll check it.
Call a private member function of a base class from the derived class.
We're not calling from a derived class. We're always going from here to here. So this one is commented out.
Yeah, but you cannot call it because leave has a type of derived and not of the middle derived.
Yeah, but we befriended, so the friend declaration here is probably the important thing.
Yeah. I don't do friend classes.
Yeah, in general, you shouldn't do that. I should probably explicitly mention that. This is to make the pattern a bit more safety friendly and not allow the users anything, but through the friend declaration, that should be possible. Yeah. Good. I also have a second example, which looks similar, but now we have 2 methods, so foo and bar in the base class, and they dispatch to foo impl and bar impl. And we now again want to see what happens when we call derived foo down here, marked with a 1. So we go up in our base class, it calls foo, we output base foo, and then we call leave foo impl. And the most derived implementation of the foo impl method is here. So it outputs middle foo impl. And then we call another method, this bar. So another method of our base class that again dispatches up here. We get the output on the console, and then it calls bar impl, which dispatches to the most derived implementation of bar impl, which is down here. So this is how you can call other methods here. So you shouldn't, currently it would be possible here to call it at place 3, also call bar impl directly. This might be one of the issues that are left here, but I will later on show how we can prevent this. So in general, you should only call methods from the base class because these are usually the outside interface. Of course, if you absolutely know what you're doing, it might make sense to go into the same class, but usually you just want to go to your base class, to the official interface of your class hierarchy. If you want to prevent that last sort of misuse that I mentioned, forget the left-hand side first, let's look at this one here. So that's the passkey idiom. We could just make a key class that's only constructible from our base class, so nobody else can construct it. And then we simply annotate all of our methods with that key class as an unused argument. And then the only way how somebody can call these methods is through the base class. So if we look at case 1 here, if foo_impl calls bar, that's of course possible. It goes up to bar, and bar then dispatches to bar_impl because it can create the key class. But if we look at this line here, this will give you a compiler error. If we try to directly call bar_impl with a key class, that's not possible because it has so it didn't explicitly put the private here, it has a private constructor. And only our friend class base can construct that key that is actually needed to unlock these methods and being able to call them. So this is sort of the bulletproof version. You don't absolutely need that. It's just if you want to make it completely safe and prevent all of these accesses through the class hierarchy that go not through your base class, then it can make sense to do something like that. And there's also a last thing missing that might go wrong. So currently you could create a base class object that is still possible. Will show later on what problems this makes. You could prevent that by making the constructors of your base class that's not being meant to be used as or being created. If you make the constructor private there, then it's not possible to create a base class object. Usually, you can only create one of the leaf classes. So the derived class here should be constructible, but the others shouldn't be. Good, now, as always, C++23 makes everything way easier. There's deducing this in C++23, and this is sort of almost all that we need to implement what I've shown before. It just falls out naturally. So if we use that this argument, the implicit this argument for each of these methods, then this automatically deduces the type to the most derived type, so to the actual type that we're calling it in. So if we create a derived class and we call a method in our base class, then this self argument has already the correct type derived. And if we then call one of the impl methods, it dispatches to the most derived version of that. So that's fairly easy. If you want details, read the proposal. Currently, that's unfortunately only available with MSVC. I hope the other compilers implement it soon too.
And I think the parents and yourself should go. This is the function at this point is an object.
Yeah, the self, exactly. The parents are incorrect after self, so they should be removed. Yeah. Correct, thanks. Good, now let's see how this looks in action. So if we want to use that with a variant approach that we saw in the beginning. So let's assume we have our derived class A that inherits from middle with derived A as a template argument. Usually there are several methods that you implement in there because you specialize them. Same for derived B. But now you might also run into the case where you want to use one of these classes in the middle of the hierarchy as an object, so being able to construct them. If you want to do that, you can just create an empty class, middle proxy, that inherits from middle with itself as a template argument, and you leave the body empty. By that, that makes it a leaf class, and you're able to construct an object of that type if this is something that you want or need. And then, again, the example from the beginning, we have a static vector with a stat variant of derived A, derived B, and our middle proxy class with 100 elements. We push back one derived A, one derived B, and one middle proxy class. And then we can just loop over the vector, call stat visit on that, and call our foo method that was the sort of the interface to the outside in our base class, in our class hierarchy. Of course, there's also another option. We could also use a classical functor. Maybe we want to make it explicit that we accept in our base class. So we use base with a template argument leave as an argument here, capture it by reference. That's important. And then we can call our foo method, and again, at the very end, use setVisit with our functor. Yeah, question?
I'm curious, in the first week, what does auto evaluates to, like, what's the type of auto?
The actual type that is in there, because yeah, the setVisit checks whether it's derived A, B, or middle proxy, and then gives you the correct type. Yeah.
I think the confusion comes from using the pointer syntax for accessing member functions.
Ah, it's again, yeah, sorry. Yeah, sorry, my bad. Again, another error code. So it shouldn't be the pointer access for value, it should be the dot. Thanks for catching that. And the same further down in the second one. So yeah. Just replace it with a dot. And that's also one thing. Well, otherwise I'll ask you the question, what would happen if I remove the ampersand here in that base leaf? I hope you haven't all read it. Any ideas? What would happen in that case? Slicing. And what would that mean? We're doing a static cast in our base class to what we think is a derived class. Sorry? Yeah, exactly. So it's undefined behavior. If you remove that single ampersand here, then you get a real value of our base class, which is no longer of the derived type. So it's an actual base class. And then our method leaf that we had in the beginning tries to cast that to the derived class. This won't be caught at compile time. It will give you incorrect results at runtime. So undefined behavior or anything can happen in that case. So you have to be careful here. But as I mentioned earlier, if you make the constructor and all special member functions in your base class protected so that only the derived classes can access that, then you would get a compiler error if you leave out the ampersand. So that's probably a good thing, making the special member functions protected in the base class or in any non-leaf class. And then you cannot run at least into that problem here. I said it can be prevented by making not only the constructors, all special member functions, so copy constructor, copy assignment of non-leaf classes protected. That prevents the problem here. Good. I got a request by a popular C++ trainer that I met last week to mention something explicitly. So the usage of state variants that I explained here does indeed replace dynamic polymorphism. So we sort of don't need virtual methods and dynamic polymorphism with that. However, please don't call it static polymorphism. So it's CRTP itself is static polymorphism, but as soon as you put it inside a variant, it's no longer static polymorphism. I'll explain a bit why. So we have sort of both aspects in one pattern. So dynamic aspects of the pattern are that setVisit uses dispatching via usually function pointer tables. So there's really a dynamic dispatching depending on what's actually in there. But on the other hand, there are also static aspects of the patterns, as I mentioned. So the supported types have to be known beforehand. So you have to know what you want to put in the variant. There's no way to extend that afterwards. The memory consumption has to be known. That's sort of implicitly done by the supported types. It's just the maximum size over all types in the variant. And on the other hand, once the dynamic dispatching via setVisit is done, afterwards it uses static dispatching. So then you're completely dispatching in a static way. But before that, there's one dynamic dispatch in setVisit, as I said, usually via function pointer tables. So coming back to the animal examples from the very beginning, this pattern is effectively a chimera between static and dynamic polymorphism. So something in between, neither one nor the other. And that already brings me to the end of my talk. Thank you very much for listening. Looking forward to your questions.